Hi everybody, Cal here with the last section of the course, 6.3 Orthogonal Projections. So, if you were following what's going on in 6.2, this section should not be a very big stretch. Before we talked about a projection onto a vector or a line, here we'll talk about a projection onto a subspace. And the idea is, if I've got an orthogonal basis for some subspace, the projection onto that space is going to be pretty much exactly what you think it's going to be. If you follow through example 1, it shouldn't really be a shock. And theorem 8 is going to be the main theorem here. The formula that they give you here is exactly the formula that you think it would be if you've been following what's going on. There's a note here, which is that you do need an orthogonal basis of W in order to use this decomposition theorem. So this is called the orthogonal projection of Y onto W. And example 2 lets us compute one in a very unsurprising way. Geometric interpretation should follow from the formula. But do read through that section. That's relatively important. Properties of orthogonal projections. So the first blurb is true and important. Theorem 9, the best approximation theorem, tells us how to find the distance from a vector to a subspace. And example 3 and 4 play with those ideas. Theorem 10 refines Theorem 8 in the case that we've got an orthonormal basis for W instead of just an orthogonal basis for W. The formulas simplify just a little bit. And that's really about all there is to say there. So that's our last reading for the course. I just hammered these all out in a single afternoon, so if my voice is sounding more tired now than it did in the beginning of the term, you know why. I hope you guys enjoyed the reading guides, and I will see you in class.